So this is our circuits 3 video, and in previous video in number 2 circuits 2 I mentioned about this time charging graph for the capacitor, and we did one question related to it. In this question in this video we're gonna do a few more questions with RC circuits. So on AP exam you have usually quite a few with just the capacitors and capacitors with resistors in the circuit. So I mentioned about the formula that you can use to calculate tau, or time for the capacitor to get charged to 63%. So this will give you the time in seconds or milliseconds, nanoseconds, microseconds, depending on the size of your resistor and the capacitor in the circuit. And so you're going to get the maximum charge, the maximum voltage on the capacitor when you have the maximum charge. And so let's look at some of the questions that we can use to understand better how the capacitors with the resistors work in the circuit. So in number 12 in our lessons online, you have the switch that is closed as shown, and so at first it is closed, and after a long time compared to the time constant of the capacitor, which they mean tau, what will be the current in the resistor of 2 ohm? So if tau is the time that it takes to charge the capacitor, so from the formula we have RC, and they say after the long time after the switch, so here is the switch S, is closed, so that means long time after the capacitor has been fully charged, what will be the current in 2 ohm resistor? So the problem does look complicated, more complicated than it is actually. So after the capacitor is fully charged, the current through the branch where the capacitor is not gonna flow. So the current is only gonna flow through the wires that I drew in red, because the other one where the capacitor is disconnected, because the capacitor is fully charged and there is no potential difference between the battery and the capacitor plates. So the current cannot go this way, so it's the same as being disconnected completely. So what you have is just the circuit with 2 resistors. So you have one resistor which is 2 ohm, and you have another resistor which is 1 ohm. So the total resistance of 2 resistors in series is 3, and the current is equal to the voltage divided by the resistance from Ohm's law. So the voltage is 6 and the total resistance in the circuit is 3. So the current is 2 amps. So you see the question is pretty easy. Often it's worded like it looks complicated, and also you're not used to use capacitors in your circuits. So every time when they say long time after the switch has been switched, then you look at the circuit when in the capacitor and look at it if it is fully charged, and if it's fully charged then the current cannot flow through it because there is no potential difference between the capacitor and the battery. So the current stops floating through the capacitor. It only flows through the capacitor when the capacitor is charging. In this question, number 13 from our online lessons, they say that uncharged capacitor and a resistor are connected in series to the battery of EMF of 12 volt. The capacitor is 5 microfarad, resistor is 8 × 10⁵ ohm, and they want you to calculate the time constant. So if I wanted to calculate the time constant, it is R times C. So R is 8 × 10⁵, and the capacitor is 5 micro, 10⁻⁶. So that gives you 4 seconds. It's going to take 4 seconds for the capacitor to be charged 63% of its full maximum charge. Then they want you to find the maximum charge on the capacitor. the maximum charge on the capacitor will happen when the capacitor is fully charged. When the capacitor is fully charged, then there is no current flowing, and the capacitor, the voltage dropped in the circuit, all drops on the capacitor. So if I want to calculate the charge on the capacitor, the maximum, it is the capacitance times the voltage, because the formula for the capacitance is how much charge per voltage. So times both sides by V gives you capacitance, gives you the charge is equal to capacitance times the voltage. So the capacitance is given 5 micro, and the voltage is given 12. So the maximum charge on the capacitor is going to be equal to 60 microcoulombs. And then for the next question, they ask you the charge on the capacitor after 6 seconds. To calculate the charge on the capacitor after 6 seconds, I'm going to use this formula. So it is the maximum charge, and then they have 1 minus the E, the constant, 2.7, and to the power of negative T time, which they give you 6 seconds over RC. So if I want to, so this was A, this was B, and for C, we have the charge on the capacitor after 6 seconds is equal to the maximum charge, and I have 1 minus E to the power of negative time over RC, or time over tau, which is 4 seconds. So we have the maximum charge, which is 60 micro, and then I have 1 minus E to the power of negative 6 divided by 4. And the charge on the capacitor after 6 seconds is equal to 46.5 microcoulombs. Next question, they ask you to find the potential difference across the resistor after 6 seconds. So the potential difference is voltage for D. So the voltage, again using the formula, is going to be equal to the charge on the capacitor after 6 seconds divided by the capacitance of the capacitor. So that is 46.5 micro, which is 10 to the negative 6, divided by the capacitance of the capacitor, which is 5 10 to the negative 6, which is also micro. So I can replace this micro with 10 to the negative 6 to see that they can be cancelled. So negative 6 can be cancelled, and I have 9.3 volts. So that is the voltage on the capacitor, and the total voltage in the circuit is given as 12 volt. So if I have 9.3 volts dropped on the capacitor, then on the resistor is going to be 2.7 volt, the rest of it, because the total voltage that has to be dropped is 12 volts. And 9.3 and 2.7 makes the total voltage dropped that is leaving from the battery. And then the last one, the current in the resistor at that time. So if I'm calculating the current in this resistor at the time when the voltage is 2.7, so for E, the voltage on the resistor after 6 seconds is 2.7 volts, and I need to calculate the current through the resistor. So that is the voltage divided by the resistance. So the voltage is 2.7, and the resistor is given 8 10 to the 5th. So this is 8 10 to the 5th. And that will give me approximately 3.5 microamps. So that will be the current through the resistor after 6 seconds when the capacitor is not fully charged yet. Here's the question that I found on Montreal Institute of Technology, and I always suggest you to watch those videos. They are the best prep videos for AP exam, and the links are on the web page, and I can also add the links in the description of this video that I highly suggest those resources for preparation for AP exam. And so here I have 24-volt battery is connected to a switch, an ammeter, a 6 ohm resistor, and 1000 microfarad capacitor, or 1 millifarad capacitor, and a 12-volt resistor, a 12 ohm resistor as shown in the picture. The switch is closed at the time t equals to 0. What is the current indicated by the ammeter alone time after the switch is closed? So here's the trick again. If they say alone time after the switch is closed, that means the current is not flowing through the capacitor. So if they want you to find the current, I can use Ohm's law. So I have V is equal to IR. The voltage is 24. I'm looking for the current, and the total resistance in the circuit without the branch that has a capacitor is 12 ohm. So the current is 2 amps. Again, you see that the question looks way more complicated than it is, and the keyword right here is the long time after the switch has been closed. So if there's a long time after the switch has been closed, you completely erase the branch that has a capacitor because it's fully charged, and then you have the current flowing only through the rest of the circuit, which gives you 2 amps in the circuit. Here's one more question that we're going to look at, and in this one you have 10 ohm resistor, 15 ohm resistor, and 40 ohm resistor are connected as shown to a 48 volt EMF source with internal resistance of 1 ohm. And what is the terminal voltage of the EMF source? So in this case, we don't have a capacitor, we don't have to worry about the capacitor, so all we're gonna do is to calculate the terminal voltage, or the voltage between, I'm gonna mark this point A and this point B. So the terminal voltage is going to be the voltage between the points A and B, and this is what I'm looking for. So at first I see that these two resistors are connected in parallel, so I can find their total resistance and replace them with one resistor. Then I have 15 ohm resistor, so here I have 15 ohm resistor, and then I have the battery, the internal resistance of the battery, and the rest of the circuit. So this one is 15 ohm. I need to calculate the total resistance of this branch together. So I have 1 over plus 1 over. That will give me times the top and the bottom of the second fraction by 4. So that will give me 5 over 40. And so it's 1 over, your result, flip over. So if I flip it over, then I get 8 ohm. So this one is 8 ohm. And this one is 1 ohm, the internal resistance, and the EMF is 48 volt. So if I'm calculating the voltage, at first I need to find the current. So the current in the circuit is equal to 48, the total voltage in the circuit, or the EMF, divided by the total resistance, and the total resistance is 15, 8, and 1, which gives me 24. So the current will give me 2 amps. And if the current is 2 amps between the point A and B, so here is your A and here is your B, I have this total resistance. So the total resistance here of this part is equal to 23 ohm. And the current we said, so I'm going to say here is the current flowing in this direction. So the current we said is 2 amps. That means the voltage that is dropped outside of the battery, so here is the battery. So the voltage that is dropped outside of the battery is the total resistance times the current. So 2 times 23 is going to give me 46 volt. So the terminal voltage AB is equal to 46 volt. Yes, don't choose C every single time just because you do not know how to solve the question. You always have to solve the question. So in this case, it is C and it is 46 volt. I feel like these questions are more AP Physics 1 type of questions, but let's review them anyway because they are useful to know how to solve. And in this question, we have two 10 ohm resistors and 40 ohm resistor are connected as shown to a 100 volt EMF source with internal resistance of 2 ohm. And how much power is dissipated by the 40 ohm resistor? So we have to do the same calculations. We know that from the previous problem that if I calculate this total resistance right here, I'm gonna get 8 ohm, and this resistor is 10 ohm, and this resistor is 2 ohm. So the total resistance in this circuit, the total resistance is 10 plus 8 plus 2 gives me 20 ohm. Then I can calculate the current, which is the total voltage in the circuit, which is 100. So the voltage divided by the total resistance, that will give me 5 amps. Then I can calculate the terminal voltage in the circuit. So I know, or actually the voltage dropped on every single element. So the voltage dropped inside of the battery before it even leaves the battery is the current times the internal resistance, which is 10 volt. Then the voltage dropped on this resistor, again the current, which is 5 times 10 gives me 50 volt. And in this case, the last one between those two resistors, or between these 2 points, it is the total resistance, which is 8, times the current, which is 5, gives me 40 volts. And if you add them all together, 10 and 40 and 50 should give you the original EMF voltage, 100. So voltage is dropped as you move along the circuit, and if you had 100 volt, you have to drop 100 volt before you get back to the battery. So if I have 40 volts dropped between these 2 points, the ones that are in blue, then I know the voltage and the resistance for this 40 ohm resistor. And they ask me the power dissipated by the 40 ohm resistor. So the power is equal to I times V. And I don't have the current through 40 ohm resistor. I could calculate it, but I also can convert this formula into, if you replace, so V is equal to IR. If you replace V with IR, then you also get the power is equal to I squared R, or you could say I is equal to V divided by R. Then the power formula can also be V squared over R. And I'm going to use this formula for my calculations of the power because I have the resistance and I have the voltage. So the power on 40 ohm resistor is equal to V, which is 40 squared, divided by R, which is 40. So the power on the 40 ohm resistor is 40 watt. And that would be B. In this case, we have 2 parallel plate capacitors C1 and C2 with different capacitances are connected in series to a battery and allowed to charge fully. If C2 is twice the capacitance of C1, which of the following statements must be true? So I'm going to draw a circuit with the battery, and then I have one capacitor, and I have another capacitor, and here is EMF, and then I have C1, and then I have C2, And then they say if C2 twice the capacitance of C1, so that is twice of C1, which of the following is true? So let's look at every single one of them and analyze what we see. So the potential across the plates of each capacitor must be equal. That is not true because they are not parallel. The charge located on the capacitor C2 must be twice the charge located on the capacitor C1. That is also not true because in series connection, the charge on each capacitor is the same. The electric potential across C2 must be twice the potential across C1. And when I say electric potential, I mean voltage. And the voltage formula is voltage is equal to the charge over the capacitance, because the capacitance is equal to the charge over the voltage. So I can derive this formula. And because V1 would be, they have the same charge over C1, and V2 is equal to charge over C2. But C2 is twice C1. So C2 is twice C1. So that means C1 voltage on the first capacitor is larger than the voltage on the second capacitor twice. And they say the electric potential across 2 must be twice the electric potential C1. So that is not true. The electric field strength across C2 must be twice that of the field in C1. An electric field, if you remember that the voltage is equal to the work over the charge, which is the force times the distance over the charge, which is electric field times the distance. So we know the voltage and how they compare with each other, but we do not know anything about the distance. So we cannot talk about the electric field of each capacitor because we do not know by how far they're just separated, so that wouldn't be true. And then the last one, they say that the energy stored on C2 must be half that of energy stored on C1. And I did not give you the formula for the energy. So the energy, or the potential energy of the capacitor, is equal to 1/2 Q squared over C. So that would be the potential energy stored in the capacitor. Have not seen many questions on AP exam related to this formula, and we hardly ever speak about this formula in the classroom as well. But if I wanted to calculate, then I see that electric potential energy stored on the first one is equal to 1/2. They both have the same charge squared divided by C1. And electric energy potential stored on second capacitor is again 1/2. And then I have the same charge Q squared divided by C2, but C2 is twice C1. So that shows us that potential energy on the first capacitor is twice as much as the potential energy on the second capacitor, or the second capacitor has half of the energy of the first one. So this is where E is the correct answer. And if you have anything like this on the AP exam, it's going to be with a multiple choice like these questions. And again, I really suggest Monterey Institute of Technology AP Physics 1 and AP Physics 2 lessons, because they have these type of questions for you to practice, and very useful questions and very strong questions for AP exam. Here's another question. This one is with the capacitors. So two parallel plate capacitors, C1 and C2, of different capacitances, connected in parallel to a battery as shown in the switch is closed and the capacitors are allowed to completely charge. C1 has plates of area A1 separated by distance D, and C2 has the plates of area 2 times A, twice the area of the first one, also separated by the same distance D. Which of the following statements is true? So the formula for the capacitance is equal to K is the one that depends on the dielectric, and then we have the electric constant, or the one, the permittivity of the vacuum, and then we have the area and the distance. So the capacitance of the first one is equal to, and if they're both in vacuum, so I'm going to say A sub 0, and then the area over the distance, and the capacitance of the second one is equal to the same material as for dielectric, and then I have twice the area and the distance. So it looks that the capacitance of the second one is equals to twice the capacitance of the first one, but the voltage that they have is the same because they're connected to the same battery. So the voltage between point A and B is the same for both of them. And now if we look at our answers that they give us, let's look at them and analyze them. So for A, they say the capacitance of 2 is 4 times the capacitance of C1. That's not true. C2 has half as much charge on its plates. So the charge can be calculated as on the one is C1 times V, and the charge on the second one is C2 times V. And so I see that C2 is twice as much as C1, so the charge of 2 is equal to twice the charge of 1. So let's look at B. C2 have half as much charge as C1, not true. And then for the next one, they say C2 has twice as much potential across its plates. Potential difference is the same for them because they're connected in parallel, so that is not true. For D, C2 has an electric field across its plates equal to that of C1. So again, the voltage is equal to E times D from the previous question, and electric field is equal to the voltage over the distance. They both have the same voltage and they both have the same distance. So it looks like D is right. C2 has electric field across the plates equal to the C1. And then the last one is C2 has half as much energy stored as C1. And if you remember the formula from the previous question, it's equal to 1/2 the charge squared divided by the capacitance. And so you have for U1, you would have the charge on the, so let me rewrite it like this, 1/2. And charge on the second one is the charge on the first one. So I'm going to say Q1 over C1, and the charge on the potential energy of the second one is 1/2, and I have Q2 over C2. So if I plug in my numbers, I have 1/2 Q squared, 1 squared divided by C1, and then Q energy on the second one is 1/2, and Q2 is twice Q1, so squared gives me 4 times Q1 squared, and divided by C2, which is twice C1. So it looks like potential energy of the second one is equal to twice the potential energy of the first one. Let's read the question again. It says C2 has half as much energy stored as C1, and that is not true. C2 has twice as much energy as C1. So the only answer for this question, the right answer would be D. C2 has an electric field across its plates equal to that one of C1. This will complete our Circuit 3 video on capacitors and resistors, and circuits with capacitors, circuits with resistors, and circuits with capacitors and resistors together. Thank you for watching this video, and I will see you in the next one.